Yeah, welcome to our Compass seminar this Wednesday, again in Slab 103, with some real people in the audience, although we don't have very many people here, to be honest. We have an invited speaker today, Alok Bhargava from the University of Maryland School of Public Policy, where he is a professor. His background is he got a bachelor's degree in mathematics from Delhi University, and then some degrees up to a PhD degree in economics and econometrics from the London School of Economics. Then he has several professor appointments. He is starting as an assistant professor in economics at the University of Pennsylvania, then University of Houston, University of Texas School of Public Health, again University of Houston, Harvard University as a visiting professor, faculty affiliate for women's studies at the University of Houston. Then he spent time with the World Health Organization. That's where he got in touch with our president, Julio Frank, right? Many years ago, 1999. So that's a connection to the University of Miami in some way. Then he was as a visiting professor at the University of Paris. He was in South Africa. He was a faculty affiliate at the Texas Obesity Research Center. And then he went to the University of Maryland. He has published more than 80 papers, so he is an economist and working on health issues, so most of his papers focus on those things: nutrition, food policy, population health, child development, demography, epidemiology, AIDS, finances in developing and developed countries. There are also 2 books or so. He's also an editor of a founding editor of a journal called Economics and Human Biology. And now in the last few years, in addition to these health and economy-oriented studies, he has started to do some work in the field of oceanography and climate research. And so he wanted to present that to the audience here at Erasmus, to the climate research community and oceanography community, to get a little more in touch with us and discuss these issues a little more. So the presentation that he will give today, I will share the screen now, is here, entitled Sea Surface Temperatures, Sea Ice Thicknesses, and Ocean Surface Current Velocities. Please.
Thank you very much for inviting me. It's a pleasure to be here. I understand with the COVID pandemic, most places are holding seminars remotely, but that's fine. So we've got used to Zoom. So let me this is my second paper, as it were, on global climate issues. But the first one just appeared in the journal Royal Statistical Society. I'm just going to present a diagram. Oops, this is not this way. It's not moving down.
It doesn't work? Maybe you need to click into the PowerPoint window one time.
Oh, okay, it did.
Okay.
Thank you. So I will present some of the basic model from the previous article in a few minutes. But we all know that anthropogenic activities have increased the emissions of greenhouse gases such as carbon dioxide, methane, nitrous oxide, and it's known from Arrhenius in 1896 that they're likely to increase the ambient temperatures, and that's the position of the IPCC report 2014 as well. But I think that there's been less emphasis on the absorption of CO2 by the oceans, and it is actually quite difficult to assess the carbon content, especially at lower depths. I have a letter in Science, e-letter, on why we need to go beyond just looking at carbon dioxide concentrations in the atmosphere. Now, more recently, IPCC 2019 has emphasized the role of cryosphere and oceans and so on for climate mitigation policies, in particular warming of oceans. Now, it's likely that sea ice thickness and also glacier thickness are going to start decreasing due to higher ambient temperatures and water temperatures, and the whole emphasis of IPCC on holding temperatures below 1.5 degrees centigrade is probably a very minimal condition, and it may not be adequate for maintaining, global sustainability, in the sense that we could see global temperatures really spiraling out of control, as I'll argue in a few minutes. So this is a diagram from my earlier article, and those of you who are in social sciences will know that industrial and agricultural activities, transportation, population, these are data from the World Development Indicators, and these lead to carbon dioxide emissions. Now those are reported in the Edgar databases based on what the countries are reporting. So again, there can be serious measurement errors, misrepresentation, and so on. But anyway, the carbon dioxide concentrations in the atmosphere are actually much more substantive indicators in some sense. Now, the Scripps Institute has about 10 stations, 6 in the northern hemisphere, 4 in the southern hemisphere, but the WDC-GG database actually has something close to 125 stations for measuring the carbon dioxide in the atmosphere. I'll come back to that a bit later on. Now, that's likely to affect the ambient temperatures. Now, the whole emphasis in my research is actually on actual data sets. There are no projections used, and unlike much of the climate science research, we're not really making any assumptions without verifying them to the extent possible. So so these ambient temperatures data are from the weather stations. Now, there could be possibly up to 85,000 weather stations, but most of them are dropped from time to time and so on. So we have data on about 10,000 weather stations generally. Now, this atmospheric concentrations will also, of course, affect ocean acidification by lowering the pH factors, and that's a very important aspect. And in the World Ocean Database, we actually have something like 400,000 oceanographic stations where we know the oxygen content of seawater, as well as pH levels, salinity, and so on. Now, glacier thickness, of course, is likely to be affected by ambient temperatures. Now, there's the GLATHIDA database, but I've not got any results on glacier thickness because the GLATHIDA database actually measures the glacier thickness at various points, but not frequently enough over time. So, what are the time trends? It's very difficult to figure that out. And there's, of course, sea ice thickness, and that's the data set put together by the Copernicus website, and that's what's analyzed in this paper. Now, if you have any questions from time to time, I'll be glad to pause, but otherwise I'll try to wind up in 45 minutes as Ronald asked me to. But feel free to interrupt. I don't know how that works on Zoom, but so we know that emissions, heat emissions from land and dumping of industrial and agricultural waste and plastic in rivers and oceans is likely to increase sea surface temperatures eventually and reduce sea ice thickness, because the freezing points are going to be much lower when you have lower pH levels in the sea waters. Now, Hyman and Rickenstein had made this point about the feedback effects, and they are talked about a lot in the climate literature, but I have not seen them in the format that I will be presenting some results to you in a few minutes. And so, for example, if sea ice thickness starts to decline, then in the future periods, is it the case that sea surface temperatures are actually higher as a result of lowering of sea ice thickness? And I'm going to present some results here which will show that's indeed the case. And then there's this issue of ocean surface current, zonal and meridional velocities. They are likely to be affected by higher sea surface temperatures, but these ocean surface current velocities are really a bit complicated to model, as I'll explain as we go along. And part of the problem is that we don't really have very much evidence on the interactions between deep ocean currents and sea surface currents. Now, let me just say that I've learned a few things about measurement. Most of you are much greater experts than I am. The only reason I actually want to understand the measurement issues is because otherwise I cannot model the interrelationships between the variables. So if you're doing something and producing these remote sensing data, I need to understand exactly how you produce them, because otherwise I can't analyze them. So again, it's important to analyze the interrelationships between sea surface temperatures, sea ice thickness, and ocean surface current velocities for a common grid size. Now, what grid size should we choose? I'll just discuss that very briefly as we go along. But they're available at different grid sizes, and I'll just show it to you on the next slide in a few seconds. So again, the time frames are actually important. So I know the IPCC is emphasizing that if we can keep CO2 concentrations below certain levels, and the ambient temperatures, the global average ambient temperatures don't go up by 1.5 degrees centigrade, everything will be fine. But that's a very broad statement to make. I mean, what do you mean by global ambient temperatures? I mean, there's the northern hemisphere, there's the southern hemisphere, there are the 4 seasons in these hemispheres. So in my previous article, I've actually criticized this practice of using a single temperature. I know it is very intuitive to explain to people that temperatures are rising, but this whole idea of temperature anomalies has some statistical issues, and I'll not go into it here, but it's published in the Journal of Royal Statistical Society this year. Now, we know that the Atlantic meridional overturning circulation takes about a millennium to complete a cycle. It may take more. In fact, it may even be that there is not a single current, but there are multiple currents there. So again, if there are changes in the Atlantic meridional overturning circulation, it would take a long time before we know what exactly happened. And I think there are quite a few articles in the climate literature on these issues, and nobody really knows what the interrelationships are. So even though I think my work is very approximate and hopefully makes sense to climate scientists, but the point is that somebody has to start somewhere to see what these interrelationships are. I like the paper by Stomel in 1948, recognizing very modestly that the partial differential equations were not going to describe seawater movements so easily. They were very crude approximations, and in fact in this article we'll see that at least the evidence points to combining zonal and meridional velocities as the eddy kinetic energy, and I'll come to that later on. So essentially then we are analyzing quarterly longitudinal data between 2000 and 2019, and differently or separately for northern and southern hemisphere, and using 1 degree by 1 degree grids. Now, so there are 64,800 of those grids. They're very vast, of course, but they could be finer, as I'll just point out in a minute. But there are other problems as well, because we know from Gauss, for example, how from this differential geometry and so on, we really shouldn't be constructing these simple 1 degree by 1 degree grids, because they are really very different at the equator versus at the North Pole, and because of all these longitudes meeting there. So I think there are quite a few mathematical topics here which I have not seen anybody actually address. I'm just trying to do some very crude approximate analyses which don't make any assumptions about any sort of parameters. Rather, they estimate all these parameters using the actual data that are available. So monthly longitudinal remote sensing data from satellites were analyzed between the years 2000 to 2019 on sea surface temperatures, which are available at 0.5 by 0.5 degree grids, sea ice thickness, which is available at 0.01 by 0.01 degree grids, and ocean surface current velocities from the OSCAR database that are available at 0.33 by 0.33 grids. So that could be the largest sort of grid we could use, but here I've analyzed 1 degree by 1 degree grids because we also wanted to look at some of the particulate matter, and those were available at 1 degree by 1 degree. So at least it's a starting point. Now, as I said, these grids are very large, everything is very approximate, but at least we can learn from the data what is happening in these past 2 decades, and taking into account differential patterns in the northern hemisphere versus the southern hemisphere, and perhaps more importantly as well, the seasonal aspects. Because of the tilt of the earth, we obviously have very limited sort of discussion we've had in the past about, is it the case the winters are becoming warmer, is it the case the summers are becoming even warmer, and so on, and how does that affect sea ice thickness and different sort of densities of snow ice and so on. How are all those things affected? Now, as I said, we're using primary data to the extent possible, remote sensing especially because it requires a lot of processing, and trying to see what is going on in both hemispheres. So for example, sea surface temperatures are based on signals from 11 advanced very high resolution radiometers and 3 along track scanning radiometers. There's an article by Merchant et al. Which discusses some of these issues. Now, one of the things is that they are what they call the interpolations are based on a Markov process, but I think it's closer to the Kalman filter, which was really an application of a problem or a solution to a problem that Norbert Wiener had raised in 1949, and Kalman actually resolved it. These are available, the so-called level 4 data, in the Copernicus database, and they can be downloaded from there. Now, sea ice thickness data come from combining signals from the ENVISAT and Cryosat-2 satellite platform. These are level 3 data, and in fact, they are approximated by the density of snow and snow depth minus the density of seawater and the freeboard, and it's divided by the difference between the density of seawater and ice. So clearly there are quite a few approximations in processing remote sensing signals, and I think Wiener was really the pioneer in this field to a considerable extent. But Wiener also made quite a few points about analyses, which I think climate scientists I've not seen such detailed discussions of them. So essentially then it's true that ocean surface current, zonal and meridional velocities are functions of sea surface heights, wind stress, sea surface displacement, depth, eddy viscosity, vertical shear, and buoyancy force. Now the problem is that we need to understand some of these things because the buoyancy force is actually influenced by changes in sea surface temperatures, and so we get this kind of a dependence which is introduced in trying to model these interrelationships. And so that is the reason why I try to understand exactly how these variables were constructed. And in fact, I found to my surprise that the eddy kinetic energy, which is, of course, as most of you know, is the sum of squared zonal and meridional velocities, is actually quite a good measure for looking at changes in the northern and the southern hemisphere in seawater movements. Now, from a mathematical point of view, it's either the complex conjugate or, so it's relatively straightforward concept, but it has been used in many applications in climate research, and I'll show you that it actually works quite well compared to the zonal and meridional velocities. So, to keep things in time, so we can estimate models which are dynamic, which depend on the past, as well as static models which actually just explain variables based on the current levels of the explanatory variables, and we can allow for grid specific heterogeneity, and we can use these econometric and statistical methods for comparing models or estimating all these models and comparing models for zonal and meridional velocities versus eddy kinetic energy. So just to give you a brief idea here, sea surface temperatures are a function of, say, latitudes, longitudes, and then there are these indicator variables for the various years. and it's a dynamic model, so they depend on the past level of sea surface temperature. So we want to see what is happening to sea surface temperatures, quarterly sea surface temperatures in the northern and the southern hemisphere over time between 2000 and 2019. It's a random effects model, and I'll try to minimize on discussing the statistical aspects unless you're interested, and I can bring them up later on. Similarly, there's a model for sea ice thickness, which again depends on variables like latitude, longitude, and the year dummies. And also we want to see sea surface temperatures, how do they affect sea ice thickness. And clearly, if sea surface temperatures are going up for various reasons, we expect a decline or a negative association with sea ice thickness. So that's generally the models, and I'll just skip all the statistical and econometric models and present some results to you, and be glad to answer any questions that you have. So the sample means in the paper are actually estimated or presented every 3 years, but here I've just done it for year 2000 and 2019, and they are by quarter. So there's quarter 1, quarter 2, quarter 3, and quarter 4 in the northern hemisphere. And generally it is the case that sea surface temperatures are going up, and we are using data on quite a few grids, something like 15,000 1 degree by 1 degree grids to up to 20,000. Now similarly, they are going up in quarter 3 and quarter 4 as well. Now it is true that the year 2000 was a bit actually a warm year, and one of the problems with using temperature anomalies, for example, as is done in climate literature, is that you're computing a sample mean which happened much earlier. And so all these deviations, the so-called temperature anomalies, are actually going to be positive. By contrast, if you look at data, in a continuous time frame between 2000 and 2019, in some years sea surface temperatures may actually go up, and in some years they will decline. But overall, the trend is, of course, in the positive direction. So similarly, we have these results for the southern hemisphere, quarter 1, quarter 2, quarter 3, and quarter 4. And let me just summarize what these results actually indicate. First of all, paired t-tests showed significant increases in sea surface temperatures and decreases in sea ice thickness between 2000 and 2019 for all quarters in northern and southern hemisphere. Now, the zonal and meridional velocities did not show significant trends in the hemisphere. And one of the problems with the Oscar data set, I think, is that even though you think you're measuring the zonal versus meridional, actually there are a lot of zero values. And so really, in some sense, eddy kinetic energy makes a lot more sense, and it actually increased significantly between 2000 and 2019 in the northern hemisphere, and though the changes were not significant in the southern hemisphere. Now again, these are very approximate. We are talking about 1 degree by 1 degree grids, which may be covering something like 5,000 square kilometers at the equator, and of course much smaller areas in the northern, on the North Pole and the South Pole. But still, it actually gives us some idea as to what is going on using actual remote sensing signals from various satellites, and putting them all together at the grid level. So here are some estimates for sea surface temperatures in the northern hemisphere in quarter 1 and quarter 2. The main point I'm trying to make here is that if you look at the indicator variables for year, many of the years, they sometimes are positive, the coefficients sometimes are negative, but in the more recent years, 2017, 2018, 2019, they are all actually positive. And so the sea surface temperatures are going up in quarter 1 and quarter 2 in the northern hemisphere, as well as, if you can see, in quarter 3 and quarter 4 in the southern hemisphere. Now, these are fairly stationary processes in the sense that the lag-dependent variables are actually quite small, but there's a lot of heterogeneity across grids, which is not surprising, even though we are controlling for latitude and longitude. So this between to within variance ratios are really quite high. And now in these models, we actually have another model, an extended model, where you include the lag sea ice thickness. So if the lag sea ice was, say, higher, then the sea surface temperatures would be lower. In all quarters, we see this result. So, people have argued about feedback effects, and these are elasticities because they are in logarithms. So essentially then, we are saying that, if you increase, let's say, if you decrease sea ice thickness by, let's say, 50%, you might see, a small increase in sea surface temperatures, something of the magnitude. So if it's going up by 50%, maybe it's going up about 3% or so. But in a minute, I'm going to show you that these elasticities, these proportional effects, are actually very large in the context of sea ice thickness. I'm going to just show you that in a minute. But these are very much elasticities that we estimate in economics, in nutrition, in health, and so on. They're generally small, but there are going to be some very large elasticities coming in a minute. So let me just summarize the results for northern and southern hemisphere in different quarters. So essentially then, coefficients of indicator variables for the years were positive and significant in the northern hemisphere, showing steady increases in sea surface temperatures in all quarters. There were greater cyclical patterns evident in the southern hemisphere, which is not surprising because there's much less land mass there, of course. But overall, there were significant increases, especially in the recent years. The lag-dependent variables imply, this process is a fairly long, stable process, and the between to within variance ratios show that there's a fair amount of heterogeneity across these 1 degree by 1 degree grades, and these elasticities are relatively small. So we do expect, if sea ice thickness goes down, we do expect an increase in sea surface temperatures in the following periods. Now, the models for sea ice thickness are here, and I think the most remarkable thing is that these elasticities, so basically then what we are saying is that if sea surface temperatures go up, let's say by 10%, sea ice thickness goes down by 20%. So we're not talking about small elasticities, but you read in the papers how the polar ice is melting and how the sea ice is declining, and the reason is that the sea surface temperatures, at least from my analysis, have a very serious high order magnitude effect on sea ice thickness. So the IPCC is emphasizing CO2 concentrations, but I think that greater emphasis is needed for the oceans. If ocean surface temperatures keep going up, all the sea ice is actually going to start disappearing, especially in the northern hemisphere, but also later in the southern hemisphere. And it is often connected to polar ice, and those sheets will also start to melt. So I think that this is in some sense the magnitudes of elasticities are really much higher. In the context of carbon dioxide and temperatures, these elasticities are about 0.05, and here we are talking about something 40 times higher. So clearly, I think IPCC needs to emphasize, and I think they are emphasizing, they are inviting me to contribute something in their next report, as I sent my papers to one of the staff members there. But I think that, the cryosphere, the glacier thickness and sea ice thickness, and now ocean surface current velocities are all important aspects. So let me summarize these results on sea surface, sea ice thicknesses. So we see a significant decline in sea ice thickness in all quarters in northern hemisphere. It is also true in the southern hemisphere, except there were cyclical patterns. Now I'm going to discuss these elasticities a bit later on in the discussion. But really, we are talking about very rapid decline in sea ice thickness. Now, these results are not based on any assumptions. I'm not using any kind of parameters, estimates, and saying, well, let's assume I got them from CMIP5 or some other database, which is based on projections. These are primary remote sensing data set. I'm not making any assumptions. Now, remote scientists, including Ronald, would know a lot more exactly about the assumptions, but whatever those assumptions are, they're common to all observations, and I'm just analyzing those observations. So it's true that there are some approximations involved here too, but they are much less serious than making an assumption how sea ice thickness will respond to increases in sea surface temperatures. Now it turns out actually sea ice, these elasticities are even larger in the southern hemisphere, but by not a statistically significant amount. But the ocean currents are actually connecting these, as you all probably know quite well. Now in the paper I have actually models for zonal velocities, meridional velocities, and eddy kinetic energy. But generally the models for zonal and meridional velocities don't perform too well. And as I explained to you, part of the reason is that a lot of these values are actually zero, and it makes sense to combine them as the eddy kinetic energy, as has been done in some of the climate literature. And in fact, generally, sea surface temperatures have a small coefficient but are positive in the northern hemisphere. So as sea surface temperatures go up, we see that the eddy kinetic energy is also likely to increase. This is the case for all quarters, for 3 quarters at least, except for quarter 3 where it's not statistically significant, but generally it's statistically significant in every other quarter. Now by contrast, it's actually not significant generally, or it's negatively associated in the southern hemisphere. Now there isn't much very deep sort of an explanation here, but I think the point is that sea ice is spread much more uniformly across the oceans, across the southern oceans, and so it takes a bit longer time for sea ice to start melting. But the fact is, when we looked at the t-tests, we found that sea ice, we found that the eddy kinetic energy was actually increasing over time in the northern hemisphere, but in the southern hemisphere it was not statistically significant. Now here it is actually showing that sea surface temperatures are somehow are associated or negatively associated with eddy kinetic energy when it comes to southern hemisphere in all quarters. So again, I'll just come back to this point in a minute, but we see generally that the coefficients of the indicator variables for the years were small and insignificant in the models for zonal and meridional velocities in all quarters in both hemispheres. Sea surface temperatures were not significant predictors of zonal and meridional velocities. However, they were positively associated significantly with eddy kinetic energy in the northern hemisphere and were negatively and significantly associated in the southern hemisphere. Now, they generally provide a better fit. Now, we could devise some statistical criteria. One criterion is used in the article, and it actually shows a preference for models that are for eddy kinetic energy rather than for zonal and meridional velocities. So here's the general sort of discussion. So we can see, and as I said again, these are remote sensing observations, and there are no assumptions involved here, but we see that sea surface temperatures have increased steadily between 2000 and 2019 in all quarters in northern hemisphere, at least when we look at 1 degree by 1 degree grid. Now we could do better if we wanted to. So for example, instead of 64,000, we could have we would have something like in fact it'll be 10 times higher. In fact, for sea ice thickness, we could actually have 648 million grids, and we can process all these data. We have enough computing power, but it does require extensive computer programming and so on. So we saw that sea surface temperatures increased in the southern hemisphere, though there was some cyclical patterns evident as well. Now the elasticities, which is the proportionate increase in sea surface temperatures with respect to, let's say 1% increase in sea ice thickness in the northern hemisphere for the quarters were, minus 0.075 around there, or some were slightly smaller, and these were a bit smaller or about similar in the southern hemisphere, and in fact they are also quite similar to the elasticities of ambient temperatures with respect to CO2 concentrations. So, all these indicators are moving slowly. We know CO2 concentrations are going up. Eventually, we do expect to see increases in ambient temperatures, but I'm not talking about a simple global average, but there we looked at weather stations, something like 10,000 weather stations, and you can show that CO2 concentrations are positively associated with ambient temperatures. Similarly, we can see here that sea ice thickness in the previous period, actually, if it is lower, it is negatively associated with sea surface temperatures. So if sea ice thickness is lower, sea surface temperatures are likely to be higher. Now, so this was the point I was trying to make with the previous article. But I think what is really remarkable in this paper, and I've never seen elasticities of this magnitude. So the elasticity of sea ice thickness with respect to sea surface temperatures in the northern hemisphere was, for the different quarters were about minus 2.23, 1.8, minus 1.83, minus 1.22, and 0.06. In fact, they were even larger in the southern hemisphere, namely quarter 1, minus 3.24, 2.66, 2.94, and minus 3. So these are very large elasticities. They actually indicate that the sea ice is disappearing at a very fast rate. Now, I know many climate scientists like to make projections, what will happen in year, 21 something and 100 years from now, but I think we are in a much more urgent situation. And in fact, much of the sea ice is going to start disappearing, and with it, we will see probably the melting of polar ice also, depending on how closely connected those ice sheets are. So again, to give you a little illustration, if we have a 10% increase in sea surface temperatures, that leads to a 15% decline in northern hemisphere and almost a 30% decline in the sea ice thickness in the southern hemisphere. So I think these results are actually quite remarkable. I've never seen such large elasticities previously, and I think when we read in the newspapers why so much ice is disappearing and so on, part of the reason is that not enough emphasis is being placed on sea surface temperatures, and we're dumping all these pollutants from industry, agriculture, and so on, and eutrophication of coastal waters and lowering of pH factors is also, it lowers the freezing point of seawater, and so we are likely to see sea ice melting much more rapidly. Now, there's an article by Loeb et al. In 2021 showing that Earth's heating rate is increasing, and I think that part of the reason why it comes as a surprise to many climate scientists is because they are so focused on CO2 concentration. Now, CH4 plus N2O and so on are also important, and the World Data Center for Greenhouse Gases actually has measurements from over 100 stations, which I was planning to look at some stage. But the fact is that atmospheric concentrations are important, but then so are sea surface temperatures. So we really can't just talk about 1.5 degrees. Many economists, for example, think that if you can hold carbon dioxide concentrations to levels whereby ambient temperatures don't go up by 1.5 degrees centigrade, that will be adequate, and we need carbon tax. Now, we need all these carbon taxes, but it's certainly not going to be adequate, because that's the point I made in an article by Aldi et al. In Science. I have an e-letter emphasizing the role of oceans, and the measurement of carbon in the oceans is actually very, very complex, as you probably know much more than I do, and especially at lower depths. Now, it's certainly true that seawater movements are chaotic, as Stumel recognized in the 1940s, and eddy kinetic energy is a natural sort of a variable to model, even though we don't know the interactions between deep and surface ocean currents, and we're probably never going to know it. And of course, many people are doing important work in this field, but the oceans are so vast and deep that at least we need to recognize these factors, even if we can't produce. So for example, it's been argued by Weir et al. In 2019 that if there are changes in AMOC, that could actually decrease temperatures in Europe by something like 10 degrees centigrade, and certainly it could warm Asia and Africa. So I think that IPCC and others have to recognize that we might have millions, if not in hundreds of millions, of climate migrants. We are seeing some of this phenomena in low-lying countries like Bangladesh, for example, and population density is high. And in the future, if population keeps increasing in many of these countries and biodiversity is reduced because of increased salinity, storms, and so on, we are going to see mass migration. So this whole idea that somehow everything will be sorted out so long we can hold carbon dioxide concentration below certain levels, it's perhaps not very evidence-based. In fact, the evidence is pointing towards very rapid decline in sea ice and possibly the polar ice sheets as well. But again, I'll just make a little comment there, which is that the GLAFIDA database is not so straightforward to analyze because it focuses on glacier thickness at different points in the glacier, but not enough over time, except for some regions like Svalbard and so on. So I have some plans to look a little bit at those issues. So, but overall, the point of this paper is to say that we need to reduce sea surface temperatures by reduction in greenhouse gas emissions, in heat emissions from land. Water vapor is also important, and it's compounding the problem because of increased water vapor due to higher sea surface temperatures, and of course the dumping of pollutants and plastic in the rivers. Now there are certain sort of studies, even plastics on the beaches actually tend to increase the temperatures of seawater around the coastline, and really we need to have much greater emphasis on oceans, the sea surface temperatures and so on, because they're going to play a very important role in determining what happens. Now, of course, it's very hard to make any predictions, and if I were a climate scientist, I'd be very careful about making predictions because really a lot depends on what happens to AMOC. Now, there are all kinds of articles, some saying that AMOC's velocities have decreased to a lowest level, and but in my experience, looking at all these ocean surface currents, now you may not like the OSCAR database, but the results are not that different from satellite tracked instruments as well to some extent. So I think that a lot will depend on the temperature differentials between in the poles versus the equator, and that in turn will affect the AMOC velocities. And what happens in the future is very hard to tell. And it's certainly the case that if Gulf Stream were to change course, we might see a lot cooler temperatures in European countries and much higher temperatures in Asia and African countries. So I think that the issues of climate change are really quite complicated, and we need to look at what the evidence says. Whatever databases are available, we need to analyze them. We need to try to figure out the interrelationships. Now, journals like Science, they think of climate research as telling them what are the trends in temperatures, maybe trends in carbon dioxide and so on. But at the end of the day, human activity is driving most of these things, and most of these increases in temperatures and so on, and we need to have some sort of a conceptual or analytical framework within which we can actually study these things. Now, it is a bit adventurous on my part to look at oceans because it's really a vast area covered, but at least we have three important variables or three important indicators of climate, namely sea surface temperatures, sea ice thickness, and ocean surface current velocities. Now, the last one is, as I said, very difficult to model because the speed of changes is going to be very, very slow. But be that as it may, there is some evidence that increased sea surface temperatures in the northern hemisphere tend to increase eddy kinetic energy. And I think, we are likely to sort of go through these processes in the next few decades, and we will see increases in sea surface temperatures, decreases in sea ice thickness. But what happens to ocean surface currents, we don't, that depends also on a lot of factors, including the interactions between deep ocean currents and sea surface temperatures, and ocean surface currents. But be that as it may, we need to reduce greenhouse gas emissions and reduce the pollutants being dumped into rivers and oceans for enhancing global sustainability. So that's all I wanted to say. Thank you.
Okay, very nice. Thank you for the nice presentation. Let's see if we have questions. Probably not so much from the people in the room, but maybe from the audience in Zoom. Let's see if we can see who's there. Or is that Arthur? Do you have a question?
Yeah, I appreciate your comments, but the fact is that, I haven't seen explicit, I mean, if you look at OSCAR database, okay, there may be some other satellite tracking instruments and so on, where you have more information between interactions of, I mean, you're welcome to send me some articles on this, and I'm happy to look at them, but I think that, in terms of OSCAR data sets, at least at those resolutions, I've not seen any kind of evidence which would actually be useful. But I think the whole statistical approach is different in the sense that, we've got data from 15,000 grids. Now, you think I've got too many variables. When I present this paper in social sciences, I mean, I hardly have any variables because, social scientists are used to having 10 variables, 20 variables in a model. So, I mean, I've just got, 2 variables that I can include, sea surface temperatures and possibly sea ice thickness when I'm trying to explain ocean surface currents. So, in fact, yes, but those are basically time invariant. Oh wait, I'm trying to see if I can. I mean, those are basically time. Okay, I don't actually have those ocean surface current results.
Right here. All right, so back up to the picture that you just showed. All right, so we got 1, 2, 3, 4, 5, 6, 7 variables.
Yeah, but they're all time invariant. They're just trying to describe the characteristics of the grids.
So they're large scale averages, and now when you're doing this, going to large scale averages, all the grid points.
No, there are a number of grids, 4,000. So there are 4,361 grids, for example, in quarter 3, as you can see. And so we have data on these grids on all these variables, and we are doing a regression with all that, taking into account the possible heterogeneity across grids through random effects. So, for example, some grids may have higher sea surface, higher sea ice thickness, whereas others will have lower, and there are these unobserved variables we don't observe. So we are controlling for that using a random effects model. No, they are not the average of the coefficients. These are the coefficients. You have a continuous, you have a dependent variable which is sea ice thickness. It's being regressed on variables such as these time invariant variables which we just discussed, and sea surface temperatures that are also measured. They're actually measured at monthly intervals, but we are using quarterly averages for different quarters in the northern and the southern hemisphere. There's no averaging of coefficients. There is no such thing here. I mean, this is not a simulation setup. Yes. Well, actually, that is the observed heterogeneity, but we've also taken into account the unobserved heterogeneity. So, for example, some grades may be affected by, maybe El Nino or something else in different sort of years, and that is unexplained, in some sense unobserved, and that goes into the random effects. But as far as latitude and longitude they're concerned, I mean, those are observable characteristics which are included in the model. Yes. No, but wait a minute. I mean, you. No, in fact, what. No, well, it is true, but sea ice thickness there is 0. Or at least, it may have been transformed as 0.01 prior to a logarithmic transformation. Well, actually, you can do without. No, I understand. The point is that, it is true that there will be, some element of concentration. I mean, it's the parameter estimates are going to be driven by when sea ice thickness is actually positive, as you note in northern and the southern sort of regions, let's say poles. No, I have done that to some extent, because you see the point is that we can look at ocean surface current velocities, and we can look at sea ice thickness as well as sea surface temperatures, and that will narrow down the number of grids available to actually very small, less than 1,000, let's say, in the northern and possibly 1,500 in the southern hemisphere. And you get very similar results. I mean, the point is that things are being driven by sea surface temperatures and sea ice thickness. It's true that in the near the tropics, sea surface temperatures are going to be quite high, but the sea ice thickness is really, is obviously close to zero, or would be set to some very small number. Whereas as we move towards the northern North Pole or South Pole, it's actually going to be to have a very significant effect. So, I mean, I think there's nothing almost spurious about these, because of this idea of introducing unobserved heterogeneity in the model and estimating these models either through maximum likelihood methods or stepwise estimators. So it's not simple correlations which may be affected by some spurious nature of analysis. In fact, it's quite the opposite problem. It's very hard to show that things are statistically significantly related when you actually are controlling for all this kind of unobserved heterogeneity. No, if you send me some articles, I'll be glad to incorporate them and see how I can extend some of this work. Sure. What we can do, I mean, to count it. No, that's fine. No, what I can do easily is to drop all the zero values of sea ice thickness and run these regressions again. That would take care of the criticisms that you're making, I think.
Okay, I think let's stop it here. In particular, we have a sound issue here, Arthur. We can hardly hear you. I already turned it to full volume, but for some reason we hear almost nothing, which means the people in the video recording also will not hear this. So they are probably, when they watch this on YouTube, they are probably wondering what's going on. Oh, maybe I can turn it up more here. Can you say something again, Arthur?
Yeah, I don't know. The connection just fell out for a minute too.
So now it's better. Somehow the volume was turned up for the speaker, but not not in Zoom. So now we hear you better. Anyway, I think.
Thanks for your comments. I'll try to implement them in some way.
Okay, I appreciate it.
Yeah. So.
Rest of your research, but yeah, it's an important problem that we're looking at. So appreciate you looking at it, and I'll send you some stuff.
Thank you.
Cool.
Okay, so thank you all the people who have watched this in Zoom. Thank you again to the ones here in the room, although there are not very many today. So thank you, Alok, for coming. We will have another seminar tomorrow afternoon, so I hope I will see all of you tomorrow afternoon again, maybe in MSC 343 or again in Zoom. And then we have a student seminar on Friday, a 1 hour student seminar in the auditorium. So that's the end of the Zoom session, that's the end of my YouTube recording. And so we will turn the Zoom session off now.